The final thing about my talk is that I'm going to actually present a new tool to show what is called the optimality of Gaussian random variables. Okay, so it's kind of a new hammer that you can have in your toolbox, and so I'm going to show it slowly from simple settings to more advanced settings, but it'll take some time. So and this ended up solving something which people have been trying to solve, but it also gives simpler proofs of results which people had before. So it's a kind of a different argument, and most people would not have seen this, so I'm sure of that. Okay, so the basic idea is single-letterization arguments in network information theory and optimality of Gaussian random variables. I have one more request. I haven't put up the slides on the web. I'm sure there are going to be typos, so if somebody can I will find out typos as I'm speaking, but if somebody can just mark and tell me after the talk, it will be useful, because then I can fix it up and put it up on the... Okay, so let's start. So I'm going to start from the basics. So this is Shannon's classical model of communication. What does the model say? You have a noisy channel, which is given by a transition matrix. So it tells you what is the probability of receiving a symbol Y if I transmit a symbol X. It's a conditional probability distribution. So this is a channel. So how does one communicate over this channel? The way one communicates over this channel is, if I have a set of bits to send, I first expand the bits to correct the errors. That's the encoding function. So you do some coding on it, so you make some redundancy there. You transmit those code words over the noisy channel. The receiver receives some noisy version of xn. If it's memoryless, every bit is flipped, or every bit is transformed in an independent fashion according to this probability distribution, and you get this yn. Then the decoder, who may be at a very different place, what they have to do is they have to map it into an estimate of what was said. Okay, that's the basic model of communication. I'm sure this picture is there on the workshop poster or something, but I hope everybody understands this model. This is very basic. Okay? If you don't, you can stop. And one of the basic results of Shannon is that the maximum rate, I'll tell you what the rate is, the maximum rate that you can get across with asymptotically small probability of error is the maximum of mutual information. What is mutual information? It is just this quantity for a given joint distribution. It's P of x times this quantity. It's Q of y given x log Q of y given x over P of y. So it's kind of a divergence between two probability distributions. And if they're independent, it's zero. This, in general, non-negative quantity, it's kind of a divergence between two quantities and this non-negative quantity. And this is the expression. And in the initial part, I will show you a proof of it which is elementary, but then we'll use that proof later. That's why I'm going to go over the proof. Okay, so this is Shannon's third. So what is the rate? A codebook of rate R with block length n, it means I'm going to use channel n times, is said to achieve a probability of error at most epsilon if, okay, what is the condition? I'm assuming that the message is going to be uniform from 0, 1 up to 2 to the nr minus 1. So there are 2 nr different messages, which means if I have used n time slots, then it's r bits per time slot. So that's a rate, r bits per channel use. So I'm going to transmit r bits per channel use, but I want the receiver to reconstruct the message with probability at most epsilon. Okay, so this is so if you have, and as epsilon goes 0, that's the asymptotically vanishing probability of error. So that's a rate r. And the proof of capacity uses two mathematical tools, Fano's inequality and data processing inequality. Okay, these are the two tools, and that's how we get the capacity. And I'm going to show these tools because I know that, many of you experts know this, but there may be a couple of people who may not be familiar with these two. Okay, what is Fano's inequality? What is our metric? Metric is probability of error. So we want something that captures the fact that probability of error is small. So Fano's inequality states that if I have two random variables, say that takes values in 0, 1 up to 2 power nr minus 1, and the probability of mismatch is at most epsilon, then the conditional entropy of m given m hat is less than 1 plus epsilon nr. You can even make this better, but this is good enough for us. Or if I divide by n, if epsilon is small enough, then it's very small. It's 1 over n plus epsilon times r. Okay, how do we show this? elementary. So let me take a couple of minutes to show this. So let's denote and indicate a random variable as E. E is 0, the error is 0 if they are equal, and it's 1 if they make an error. M hat is not same as M. Now clearly this conditional entropy is less than this entropy. Why? Because by chain rule of entropy I can break this as E given M hat, this should be M hat, and M given E M hat. Okay, this is a chain rule, and this is non-negative. And you can break it up another way as M given M hat and E given M hat. So this is inequality holds this way, and in fact it's an equality. Okay, it's an equality here. But you can observe that this is a binary random variable. So a binary random variable has maximum entropy 1, and this is a random variable which, when E is 0, what is the uncertainty given of M given M hat? When E is 0, M equal to M hat, so this entropy is 0. So this is non-zero only when E equal to 1. When what is the probability that E equal to 1? It's epsilon. So it's epsilon times the conditional entropy of M given M hat. So you can put log 2 per nr, you can improve it to 2 per nr minus 1. This is just the cardinality of the set. So that's 1 plus epsilon nr. That's Faneuil's inequality, that's all it says. So that when you saw the term before, it's a very, very simple estimate of the conditional entropy. Okay, that's Faneuil's inequality. What is data processing inequality? It's again a very simple inequality. It says that if x to y to z forms a Markov chain, think of z as some processing on y, then the mutual information between x and y is bigger than the mutual information between x and z. That means as you process more and more, you lose information, which is very natural to imagine. How do you prove it? Again, it's very simple. If x to y to z is Markov, what does Markov mean? If conditional independence, then conditional independence means that conditional y, the independent or this is 0. So now you observe that ixy is ixy plus ixz given y because it's 0. This is ixyz. I can break it up by chain rule in a different order. Ixz plus ixy given z. This is non-negative, therefore this is bigger than ix. So this is data processing inequality. The proof is very elementary, but these are only two tools we'll use to prove the capacity. So it's not very hard. So let's prove the channel capacity. So we have a sequence of code books with rate r, with probability where at most epsilon and let epsilon go to 0. We want to bound the value of r rate r. The point is these code books could be given by anybody, so we don't know what the code book structure is. It could be given by somebody who claims that there is a code book r. So we cannot assume anything about the code book except that the probability where is at most r. Okay, there's a sequence of inequalities that go slowly. But before I go into the sequence of inequalities, I want to look at this Markov chain. This really captures what we do in a general code book. So what does the code book say? Here the message M. The code book says how to map a message to a code word sequence. So this mapping is what a code book should give you. This is by the channel, this is the mapping by the channel. And this mapping is a decoding map. So when somebody gives you a code book, it tells you how to encode and how to decode. So if you give me a code book, now M is uniform, so I can construct this chain of this Markov chain, and I can find joint distribution. Okay, this Markov chain is kind of inbuilt into the channel model. Okay, now once we have this, let's go back. M is uniform, so entropy of M is nr. So if I divide by n, r is 1 over n h of m. This elementary properties of mutual information conditional entropy, it's m hat plus h of m given m hat. Now I have the conditional entropy. The conditional entropy, I can bound this by Faneuil's inequality. So it's at most 1 plus nr epsilon, this is Faneuil's inequality. I have this. Now I use data processing inequality to say that this is at most x and yn, because it's just a data processing inequality. It's 1 over n I x n yn plus 1 over n r epsilon. I'm dividing by n throughout. And clearly if I bring r to the other side, it's at most 1 minus 1 over epsilon. If I let n to infinity, I have to take lim sup 1 over n I x n yn. So, and if I let epsilon go to 0, it's lim sup 1 over n I x n yn. So we know that the maximum rate is just lim sup over 1 over n I x n yn. Okay. I hope everybody knows what is mean by lim sup. Lim sup means that as n becomes large, what is the largest value kind of it takes. Okay, this is kind of what lim sup means, because sequences may not have limits, they may not have supremums, but lim sup always exists because it's a decreasing sequence of supremums. So this is so we have this expression, but what is bad about this expression? So we established that this is true. Unfortunately, this is not computable because you want to. It's an infinite dimensional problem. You're working in spaces that are going very, very large. So our goal is to show that for any n 1 over n I x n y n is at most the value when n equal to 1. Max of p of x I x 1. That's our goal to show. And this is what I'll call a single-letterization argument. And we'll use it later. But it's good to see at least one. Okay? So I hope what it's clear that I use the fact that it's a small probability error to get this bound. And then the next step is to show that this bound is at most this, and I can achieve this. So achievability part is not, I'm not going to talk about achievability part, I'm just going to talk about outer bounds, and this can be achieved. Okay, so this is very, so I'm going to show this. Let's start by showing this. Is there any questions so far? Have I gone too far? It's okay. People who have seen it is very simple. People who have not seen it maybe. Anyway, let's go. So I claim first, this is a very simple claim. Okay? It's a very elementary claim. I claim that it suffices to show that if I double the channel, it doesn't increase. That's a very elementary claim, but it's sometimes useful. It's enough to show that I don't need to go to n, it's enough to go to 2. And the reason for that is that if I show 2, then I go from 2 to 4. So what is 4? 4 is just 2 times 2. So I can break it up into 2. So 4 will follow because I replace it by q. And so on for higher powers of 2. Now lim sup and subsequence, there's some issue there, but you can actually show that, okay, this is an exercise for you. Why does powers of 2 suffice? You can sandwich it. This super additivity here, you can think, if you have m and n, you can use m, a block length m code, n code to have m plus n code. You can show it. You can convince yourself that 2 powers of 2 is enough. So it's enough to go from 1 to 2. Okay, that makes a lot of, I don't have to carry on with n. It's enough to go from 1 to 2, and this is something I'll use repeatedly. Is this clear? So, okay, so how, I want to show from 1 letter to 2 letter. Okay, I want to show that half of ix1, x2, y1, y2 is less than max of ix1. Okay, let's go over this slowly. Because I'm going to play with this term later. So ix1, x2, y1, y2 by chain rule is ix1, x2, y1 plus ix1, x2, y2 given y1. This is just chain rule. Now, y1 is the output of the channel 1. It depends only on the input of channel 1. That's a memoryless property. So I can drop this x2 because that's a Markov chain. So I can get ix1, y1 plus, what do I do second part? I just bring y1 up here. But then I'll subtract this. It's an equality. I'll subtract this. Then I observe that the output of y2 just depends on x2 because the output of a channel at time 2 only depends on the input at time 2. That's memoryless property again. So I get this exact. I can drop y1, x1. I get x1, y1 plus x2, y2 minus I y1, y2. I'm going to play with this term later. So clearly this term is non-negative. This is at most less than the maximum of the mutual information. This is less than maximum mutual information. So it's less than 2 times ix1. That's the proof. That's entirely the proof of channel capacity. Okay? So this is a Markov chain. So I can drop this. So I get back ix2, y2. From this term is exactly the same as this. And I have this. And now this term is less than max ixy. This term is less than max ixy. This term is positive, so it's true. Good? Okay. So I call this a single-letterization argument. And I'm going to show that in additive Gaussian noise channels, you get for free optimality of Gaussian distributions as a consequence of such simple argument. And this is something we have done many times, but it's an observation that missed. Okay, so we'll see why this is true. Okay. So the outline for the next part, so this is the crux of what I'm going to do for the next sometime, so next at least an hour, is I'm going to show a characterization of Gaussian variables. It's been known for some time, for many decades. I'm going to apply this to point-to-point channel capacity with additive Gaussian noise, because it's a warm-up for other settings. Then I'm going to use some mathematical preliminaries and I'm going to show the proof of the characterization. It's a very nice characterization. And it's useful to know a proof because proofs are sometimes nice. Okay. So you can again reset if you have if I miss something, you can reset because I'm just stating a fact now. So here is the characterization of Gaussian random variables. It says that if x and y are independent random variables such that x plus y and x minus y are also independent. I have two random variables such that the sum and difference are also independent. Then x and y must be Gaussian with the same covariance matrix. I mean, here I'm assuming they are vectors. So this is a statement of, so if there are two random variables, independent random variables such that their sum and difference are also independent, then x and y must be Gaussian. Okay. So this was initially proved by Bernstein, assuming in 1940, assuming some moment conditions, and then it was later generalized by Darmo and Skito. I think this was independent. These two are independent, and you will see. I mean, you will see a proof of this. It's not very hard to show, at least for scalar cases. Vectoric is not any harder. But it turns out to be very, very useful for us. Okay. Any question? Is this category clear? Is it clear that if x and y are Gaussian, this must be obvious, right? This statement is saying the reverse thing. And if this is true, then x and y must be Gaussian.
You talk about variables and vectors.
Both. It doesn't matter. And this doesn't even have to be x plus y, x minus y. It can be any linearly independent combination. But then the same covariance goes away, but they are Gaussian.
Gaussian of the same dimension.
Gaussian of the same dimension. So there's a whole literature on these kind of characterization of Gaussian. But this is all we need. Yes, but this could, here I'm assuming vector because I'll go for vectors later, but I'm going to prove for scalars. Okay, what is an additive wide Gaussian channel? Okay, additive wide Gaussian channel is a channel where the output is the input x plus a Gaussian noise, an independent Gaussian noise. Okay. If there is no power constraint in the codebook, if I can have very, very big codebooks, since the Gaussian power is constrained, I can make them very, very far apart and I can get infinite capacity. So when we talk about this channel, we normally put a power constraint on the codebook. So let P be a power constraint on the codebook. Then the maximum rate that can be reliably transmitted is, as Sharon said, it's a supreme over Ixy. Okay? But this is a well-known formula, it's half log 1 plus P. So inbuilt into this formula is the fact that the Gaussian distribution is the maximizer. Okay, this is something, and you can show this in very elementary ways, but I'm going to show you a different proof of this because it's a warm-up for the rest of the talk. Okay? So even though you know this formula, there is inbuilt a maximization problem, right? Because this is what you can achieve, and why is this maximum achieved by this? There are different ways to look at it, but here's a different way. It's a way that you may not have seen. Okay, so this is the optimizing problem we're going to show. Okay, so let's start. So setting is y is x plus z is Gaussian, and I want to determine the extremal distribution which maximizes Ixy. So let me call the maximizing distribution x star. I will show you why they exist later, and I will not show you for the rest of the problem why they exist, but you can argue there. Okay, and sometimes the argument is not easy, but that's not part of this. So which means that C is, so if there's a distribution that achieves the maximum, then C is when x is distributed by x star, it's Ixy. So what am I going to do? I'm going to take two independent and identically distributed copies of x star and call it x1, x2. Okay? The channels are independent. I'm going to take two user channel. I'm going to take independent distributions. So clearly, twice 2C is Ix1, x2, y1, y2. Why? Because x1, y1 is independent of x2, y2, and therefore it just breaks apart and you get the additive property, so you get 2C's Ix1, x2, y1, y2. That's so far so good. What is the next step? Our next step is, so this is a two-channel realization, y1 is x1 plus z1, y2 is x2 plus z2. I'm going to define two random variables x plus as x1 plus x2 by root 2 and x minus as x1 minus x2 by root 2, y plus as y1 plus y2 by root 2, y minus as y1 minus y2 by root 2, and z plus as z1 plus z2 by root 2, z minus as z1 minus z2 by root 2. What do I know? These are Gaussians because that's a noise. So these are independent random variables. They are same Gaussians, correct? Because these are Gaussians, so they are independent because, and they are, so which means, and if I just linear combination, so you observe that y plus is x plus plus z plus, and y minus is x minus plus z minus, because they're linear combinations, same linear combinations. But these two channels, I mean, this is the same channel as Z1 because same distribution. This is the same channel as Z2. So this is now a new product channel with this is the input distribution, x plus and x minus. Clear? This is, so the same channel. So this is only true when it's Gaussian, right? Because if I don't have Gaussian, this channel may be different from the original channel, right? But when you have Gaussian, the same channel, the same product channel. Because this is where we're using the fact that it's Gaussian. So we get y plus is x plus z plus, y minus x minus plus z minus, okay, the same channel. Okay, so let's see what we can do with this. So far I've done nothing, I've just done a bijection, I've done a rotation. So look at the single-letterization. 2c is I x1, x2, y1, y2. Now I claim that this is equal to I x plus x minus y plus y minus. There are at least two different ways of seeing it. First of all, mutual plane is preserved in the bijection of marginals, or you can see that it's a rotation, so differential entropy doesn't change, so mutual plane doesn't change. Either way you can see, so it's just, so these two are equal. That is just a rotation. Now I can do single, I'm now going back to the previous slide, I'm doing the same single-letterization argument. It's I x plus x minus y plus, I x plus x minus y minus given y plus, I got this, the same expression I did before. This was exactly what I did before, x1, y1, x2, y2, minus y1, y2. Same thing. But look at this. This is the input of the same channel. So this must be less than C. This must be less than C. So, but this is equal to 2C because I started with 2C. And this must be at least positive. So since this equality holds, this must be C, this must be C, and this must be 0. Clear? Which means that we have that, okay, by construction y1, y2 independent. But now we also have y1 plus y2 and y1 minus y2 independent. Right? That's what this says. They're independent. Therefore, y1, y2 must be Gaussians. Okay, we'll show this is an exercise implying x1, x2 are Gaussians. Okay, so this is a term we always throw away. But if I don't throw away the term and see what it implies to the maximizer, it implies immediately that they are Gaussians. Okay, this is clear. So I'm going to use this trick in other settings too. Okay, the fact that I can just take two copies, rotate it, and do the same single-letterization argument. Look at the things we throw away, they must be 0, and what does it imply? It gives you.
So
yes.
Rotate it by 45 degrees.
Yes.
Could you prove it by different angles?
Yeah, you could do it. Because it does. I'm just using it because of simplicity, right? You could do it any angle you want, as long as they're linearly independent, right? So you will lose the same covariance though, but we'll use the I mean, because if they're not rotated by C, you can do it anything. So this argument will work through for anything, as long as they're perpendicular.
Yeah.
You need perpendicularity because exactly for this reason, right? Otherwise you will lose the same perpendicular. So as long as they're perpendicular, it's okay. The two directions are perpendicular. So it doesn't have to be 45. It's the most natural thing to do. So I just did the most natural thing. Okay, so where am I? Yes. Okay, so now I'm going to go back to this characterization and see why this characterization is true. So you are going to get into some details. We might use some board because math is easier to follow on the board than the slides. But I have the proof on the slides, so you can do it later. I mean, so you can look at it later. Any questions so far? Okay. So there is some preliminaries I'm going to talk. So what is given a random variable x, we have the characteristic function, which is the expectation of e power itx. Okay. So x is a real valued random variable. So the characteristic function is e power itx. And there are some properties of the characteristic function that I'm going to use. I'm going to use that the absolute value phi of x must be at most 1. Why? Because this is a point on the unit circle of the complex plane. If I take the average of points on the unit circle, I must have absolute value less than 1. If I take the absolute value, it's less than the expectation of the absolute value, that's 1, so it's less than 1. That's easy to see. The other thing that may not be immediately obvious is that phi x of t is a continuous function of t. Okay? In fact, it's uniformly continuous. Okay? That means if I approach a value, it's going to be continuous. And the reason for that is because the random variable, the probability that it escapes should go to 0. It's not very hard to see. And if you don't, everybody knows continuity. I'm not going to use uniformly continuous, but I'll explain what uniformly continuous means. What is continuity at a point? It means that if I give you an epsilon, I need to provide you a delta, so that if I'm delta close to the point, then the function values don't differ by epsilon. But that delta could depend on the epsilon, it can also depend on the point. If I can find a delta that does not depend on the point, then it's uniformly continuous. Okay, I can find a delta that uniform, for just depends on epsilon, it works for every point. That's just uniform continuity. It's true. So in fact you can map it to 0. I mean, it's not hard to see, but it's a nice property. If you want to use it, you can use it. Okay, the other thing is, the characteristic function uniquely characterizes the distribution of a random variable. Okay, you see, I can invert a characteristic function to get the random variable. Okay, this you might think of this as Fourier transform and Fourier inversion and so on, but you know that Fourier inversion doesn't work for many functions because they're not. But this random variables are very nice, well-behaved functions. Distributing functions are very nice. They are right continuous. They have countable discontinuity at most. So they are very nice functions. So distribution inversion works. And I would advise you, if you have not seen a proof of this, to go see a proof of this. It's not very hard to prove. All you need is dominant convergence and Dirichlet integrals. Dirichlet integrals seem complicated. For that, all you need is residue theorem. Okay, if you have these two tools, you can prove this concept. The proof I like the best is in Varadhan's book. It's a very nice, it's a very 2-paragraph proof. I teach it in class. It's a very nice proof. The other thing which I'm going to use is the fact that if I evaluate this at minus t, at every point I'm doing the complex conjugate, so I get the complex conjugate of the phi x of t. So this is a very nice property which I'm going to use. So these are properties I'm going to use. And so what is the characterization? So x and y are independent. I'm given the x plus y and x minus y are also independent. I want to show they are Gaussians. So phi x of t, I'm going to call this to be the characteristic function of x, this to be the characteristic function of y. Okay, so instead of proving it on the slides, I'll prove it on the board, because then I'll go slow. Okay? Because it's not a hard proof, but it's nice proof. Okay, let's try. Let's see how. So I've given that x plus y, x and y independent, x plus y, I'm going to show independent of x minus y. And x and y are also independent. Okay, I'm going to use this. And I called phi x of t to be expectation of e power I t x, and phi y of t to be the expectation of e power I t y. Okay, what does independent gives me? Independent gives me the following conditional the characteristic functions. So let's take expected value of e power I t1 times x plus y plus t2 times x minus y. Okay, I claim that this is equal to expected value of e power I t1 x plus y times expected value of e power I t2 x minus y. Why? Because these two are independent. So the productive function, this is the productive function, and they're independent, they become productive expectations. Okay. Now again, x and y independent, so I can now again write this up as e power I t1x, e power I t1y, e power I t2x, e power I minus I t2y. Correct? I can, because x and y are independent, so I can break this up again. Right, this is product, so it just breaks up this product, just breaks up. So this is what? This is phi x of t1. This is phi y of t1. This is phi x of t2. This is phi y of minus t2 or phi y star of t2. Right? Phi y star of t2. because minus T2 is complex conjugate. Okay, so we have this. Now can I erase this? This is the definition is clear. So let's, okay, this is a chain of equal. Now let's go, this is also equal to, when we go this way, this is expected value of e power I T1 plus T2 x plus T1 minus T2 y. I didn't do anything, I'm just rewriting the exponent. And this is equal to expected value of e power I T1 plus T2 times x, expected value of e power I T1 minus T2 y, because that's easy, and it's just because x and y independent. This is equal to phi x of T1 plus T2 and phi y of T1 minus T2. Okay? That's by definition. So what do I get? I get equation of, I get a functional equation between of phi x and phi y. Okay? So that's what I get. So this is what I'm going to play with, and I'm going to solve this functional equation. So the functional equation I have is that phi x of T1 plus T2 times phi y of T1 minus T2 is equal to phi x of T1, phi x of T2. I'm not sure you can see it, but I hope when I move away you'll see phi y of T1, phi y star of T2. Okay. So I'm going to solve this. So let me erase. So this is what I want to solve. And I'll tell you what the solution is. It's again, the point of this exercise is to see that, I mean, these things look strange, but if you look at if you try to prove it, they're not actually that difficult to prove. Okay, so how will you solve this? This could be an exercise could be an exercise. It's not very hard. Okay. So how do we do this?
Can you separate phi x and phi y?
So you can see the way it's not hard. Okay. So let's put T1 equal to T2 is equal to some T over 2. Okay. Let's put them equal. Let's see what we get. We get phi x of T. Correct. There's sum to T. This is phi y of 0. What is phi y of 0? What is phi y of 0? 1, because e power I is 1. So times 1 equal to phi x of T over 2 square, because I have 2 times, and then modulus of phi y of T over 2 squared, right? Because I have T1 and the complex conjugate z star modulus squared, right? So I get the square of the modulus. Okay. Now let me put, so this is 1, T1 equal to minus T2 equal to T over 2. Let's put this combination. Let's get different combination. So then T1 plus T2 is 0. You get phi y of T is equal to, what do I get? I get, now this becomes phi x of T over 2 square, correct? Because they are opposite. And these two, this becomes minus, so this cancels, so I get phi y T over 2 squared, right? Because they are just complex conjugate of the complex conjugate is same. Okay, so what do I get from here? This implies immediately that the absolute value of phi x of T is equal to absolute value of phi y of T for every T. Why? Because when the absolute values they are same. So let me call it f of T. Okay, let me call the absolute, so it's a real valued function f of T. Okay, now let's solve. So if I take f, absolute values everywhere, what do I get? I get f of, okay, now I have to solve this equation. F of T1 plus T2 times f of T1 minus T2 is equal to I'm just seeing absolute values here, I get f of t1 squared yes, f of t, f squared of t2. What do I get? Yes, f squared of t2. Okay, is this clear? This is what I get. Okay, now again let's put t1 equal to t2 equal to c. Let's say t, what do I get? I get f of 2t is, this is f of 0 is 1 because the absolute values of the characteristic function is 1, is equal to f of t to the power 4. Okay? Okay, I claim this is an exercise for induction. You just put 2t and t, you can show that f of kt is equal to f of t to the power k squared. Okay, you want to do 3t, I can do 3t if you want. So f of 3, so you put t1 is equal to 2t, t2 equal to t, you get f of 3t times f of t is equal to f squared of 2t times f squared of t. So this is, I mean, 1 f of t cancels, this is f4, so it's f8, f3, f9 of t. You see? I mean, this is because f2t is p power 4, you can, so just continue by induction, you will get this, it's very easy. Okay? The power is t squared. Now you can start with t over n, so this implies that f of, say, some rational number times, or q times t is f of t to the power q squared, because I could start with t over n. So it's a trick that you would see in high school, I mean, or wherever you get. And now you have by continuity, because if characteristic function continuous, you get f of any t is essentially some constant, some e power, I'm going to write minus ct squared because it's less than 1, right? Because that's the solution. I could put t to be 1, f of any arbitrary number is just, right? Okay, last step. Maybe I went too fast in last step. Let's put t equal to 1. So what do we have? So we have f of, so this implies that for any real number rt is equal to f of t to the power r squared, right? Now I can put t equal to 1, so I get, what do I get? I get f of r is equal to f of 1 to the power r squared, right? F of 1 is some number, it's like e power minus c, where c is positive, c r squared. So that's the absolute value. Okay, this is like, so this is already you see the Gaussian coming up because that's the state of the Gaussian. Okay, that's the characteristic function of the Gaussian is exactly this. So you still need to prove one more thing, because this is just shows, we just show the absolute value. You still need to work what is the imaginary part, right? There are two parts, so we just have shown the absolute value. Okay, the rest part is going to give it. So here is the. Okay, so sorry, I just proved to you that f of t is e power minus ct squared. Okay, so what do I know? I know that phi x of t is e power minus ct squared times e power I theta 1 of t, some constant theta 1, and phi y of t is e power minus ct squared e power I theta 2 of t. Alright, that's my function. Plug this back in, you get an expression for theta 1, you get equation for theta 1. What do you get? You get theta or theta x, I should put theta x and theta y. So you get theta x, it becomes exponent, so t1 plus t2 plus theta y t1 minus t2 is equal to, and theta is an odd function because so you get theta x of t1 plus theta x of t2 plus theta y of t1 minus theta y of t2. Okay? Okay, I'm going to leave an exercise. Solve this, okay, as an exercise. Same way, you will get theta x of t to be just some a t and theta y of t to be linear and to be bt. That's the solution of this. Okay? And therefore, what is this? This is e power minus ct squared times e power iat. It is the characteristic function of Gaussian with mean A, and this is the characteristic function of Gaussian with mean B, but the same variance. Okay, that's the proof. That's the entire proof. Okay, it's as simple as that. It's not any hard. It's very simple. Just characteristic function. Okay, elementary. So don't. I mean, the point is when you see something and try to understand, it's very simple. You should look at it.
But you should know about continuous or characteristic function.
Yes, but that's some elementary probability which you should take at some point. You should take. I mean, I would advise you to take some classes where you know some probability of characteristic function. Because it gives you some. Because I'll show you something later. When you see the math terms, you need to know at least what they mean. Otherwise, it's kind of hard. Right? So, okay. So that's the. So I didn't have to go over any of them. So, but it's there in this thing. So, okay. Good. Okay. So now, okay. The thing I swept into the carpet. What is the thing I swept into the carpet? I swept something under the carpet. The x is a maximizer. I assume that x star is a maximizer, and then I could play around with it. How do I know that the maximizer exists? Because the space is a very big space, and entropy functions are in general not very well behaved. They are not very good functions. Okay? Why are they not good functions? They are actually not continuous.
Yes.
Yeah, they are. If you look at the topology of, I mean, it's a very bad function in the continuous space. For this finite alphabet, it's very nice, but in the continuous space, they are actually not very well behaved functions. So you need to be careful when you say the maximize x in continuous spaces. Okay? But this is easy actually. I mean, if you take any course in your analysis, but I'm going to sweep it on the carpet. So essentially, what you have is, suppose you have a sequence of random variables whose xn converges to the supremum. Now, okay, I'll tell you what is the idea here. Okay. What could happen in a sequence of random variables? What is the difficulty? The thing that could happen is that some mass could escape. Okay? In the end, you may be left with something which is not a probability distribution. So if you have consider a sequence of variables which takes values n, so nth variable takes value n with probability 1. At the limit, the value it goes 0. I mean, the probability escapes, right? So you need to be careful that doesn't happen. What prevents you from happening this? Why is it good here? Because we put a covariance constraint, we put a second moment constraint. Okay, that gives you that mass cannot escape. That's Prokhorovsky. You don't need you just need 1 plus epsilon moment. So there's a subsequence that converges weakly, which means that there is the subsequence that converges some limit. You just need to show that limit has the same value as this. So you can show that using additive Gaussian noise and other sentences, you can show that the YNs converge pointwise. Then you can show the entropies. So actually, if the entropies are you get 2 bounds this way, and that's how you complete the proof. I'm not going to go into this, but there is something to be done here. Okay, but it's kind of standard. So you don't need to worry about this. But I will tell you, the other thing I'll tell you is that later in this class, or maybe next time, I will claim x is the maximizer without going through this. Okay. The point is there it's much more difficult because. But if you want to look at the paper, because we spend a whole appendix trying to prove things because the topology is really, really bad for us. So you need to truncate you truncate the moments, then expand it, then use some continuity. It's difficult, but it's been done once and for all. Okay, so you don't need to worry too much about repeating it. So it's done once. Okay, anyway. So here's simple. So I think you should do this just to get familiar with characteristic functions. So here's the claim: if y1 is x1 plus z1 and y2 is x2 plus z2. Where z1, z2 are independent Gaussian noise, I want to show if y1, y2 independent, then show that x1, x2 are independent. Okay? It's a very simple exercise, but it's a good thing to get feel of characteristic. If y1, y2 independent Gaussians, then show that x1, x2 are independent Gaussians. Okay? If you use characteristic function, it's a simple exercise, but it's a good thing to know. And what is the property of Gaussian I'm using? The property of Gaussian I'm using to show this is the fact that the characteristic function of Gaussian is like e power minus ct square is never 0. The moment you have zeros in the characteristic function, you can get in trouble. You can have distributions whose outputs are independent, but input need not be independent. Okay, that's a fact I'm really using. Okay. So these are things but these are good exercises to go through if you want. Okay. So what did I show? I showed for a point-to-point channel. We showed that for a channel with additive Gaussian noise, the optimal input distribution subject to a power constraint is Gaussian, use the characteristic of Gaussian and use single-letterization arguments. Okay? It seems more complicated than the traditional technique. Okay? Why I say seems? Partly because when you use the traditional technique, you just look at, take the KL divergence, show that the maximum entropy distribution is Gaussian, but then you have assumptions inbuilt there which you're not being taken care of, right? You assume that the random variable you're taking has a density or it's absolutely continuous living measure, why is that maximized? So there is some thing that people have done before. So if you assume that in this carpet, it's similar. Okay, it doesn't matter. But the main thing is, in multi-user infinite theory, this technique doesn't get any more complicated. Whereas the traditional techniques become very involved. It involves entropy power inequality, it involves other techniques, and sometimes doesn't work. So this technique works, as far as you know, it works in all the cases where traditional techniques works, and some cases where it doesn't work. Okay, so this is at least as powerful as the traditional techniques. Okay, so that's the. So what if there are more than? Okay, so now I'm going to talk a bit more generally. So we talked about point-to-point channels, and we said that what if there are more than one sender receiver? As Michelle said, a lot of people said, can we obtain a similar capacity region? Can we obtain what is the best set of achievable rates? And the answer, unfortunately, is no. Unfortunately or fortunately, what is the good thing? The good thing is we still have lots of problems to work on, right? Because these have not been solved. The other thing I want to say is these are not as hard as people make them out to be. Okay, there's an exception. Multiple access channel, it's solved to a large extent. Okay, so I'm going to show you what I would say are the two most basic multi-user problems whose capacity we don't know. Okay, so one is the broadcast channel. It's been brought up in few talks, so let me formally define what a broadcast channel is. A broadcast channel is a channel where you have a sender who has access to two pieces of information. Let me call it M1 and M2. And he wants to transmit M1 to some receiver, let me call it Y, a decoder receiver 1, and he wants to transmit M2 to decoder 2. I'm going to generalize it later. So what does he want to do? He wants to encode this message into a sequence XN, so he wants to make some error correction scheme, so that when this receiver hears some noisy version of this, he or she wants to decode it to an estimate M1 hat, and he or she wants to decode to an estimate M2 hat, and you want it to decode so that the probability of error is small. Okay? So what is the capacity region or set of achievable rates? I want also to make a point here that, okay, Michelle Efros, I don't know, she talked about a whole bunch of network settings. There's a slight difference between this setting and the settings she discussed, because in her thing, everything you can re-encode for Y. There's no separate channel for X to Y that you can re-encode. You can only shout one thing. You cannot re-code for two separate things separately. You can only shout, and then whatever they hear is a noisy version of what you shout. Okay? In her setting, each was a point-to-point link, so you could re-encode for Y and re-encode for Z and so on. This is not that model, okay? Or this doesn't fit into her model. Okay? At the end, her model changed a bit. There it fits in. In general, this doesn't fit in. In the intermediate node, you cannot broadcast. Okay? So this is still open. A lot of things are unknown. The capacity is unknown. And so this is one setting which is unknown. So it's just a point-to-point. I mean, it's like one person. Where does it occur in practice for those of people interested in communication? It's a very natural setting. You have a cell phone tower, and the tower is transmitting information to the users. You're not interested in getting your phone call. You don't care about what other people are hearing most of the time. Okay? So that's the setting. Okay, the other setting, this was introduced by Tom Cover. The other setting is interference channel. This was introduced by Rudy Alsferi. So here, what is the setting? This was a very common setting. You have two point-to-point communication channels. This sender to this sender, this sender to this sender, this receiver. There are two point-to-point channels. The only problem is that there's interference. Okay, I'm talking to you guys, there's somebody else talking here, they interfere. Okay? So because of interference, you cannot get point-to-point capacity. What is the capacity of achievable rate regions? Okay? Okay, these are two open settings. But I also like these two open settings. I got interested into a lot of this topic because A, these problems are open, but also because there's something very, very nice about these problems for me. And what was that? For these two problems, there are achievable regions, one for each, one by Martin. Martin got a Chandra Nair award, I think a couple of years ago, and one by Han and Kobayashi, whose optimality or suboptimality had not been established for over 30 years. So you had a region which in principle could have been the capacity. People didn't know whether it's capacity or not. Okay, I have to qualify this because just recently we showed one of them, I'll tell you in the next slide. But whereas for all of both these regions, there was a way to test their optimality, suboptimality. Okay, there was a way to test if they are optimal or suboptimal. For some, and I'll tell you why people could not do that, do this test also. So what is the testing? The testing procedure requires infinite computational resources in principle. However, if it's suboptimal, then the procedure will terminate quickly. Okay, if it's not suboptimal, you keep running it. Okay, now we have a lot of computational power and you can do it. Okay, what's the procedure? Suppose someone gives you an achievable strategy such that for any channel Q, it gives an achievable region AQ, let me call it A of Q, and as n goes to infinity, the achievable region will go to the capacity region. Okay, usually this is very easy to show. In fact, for both these problems, these achievable regions have this property. Okay, so now we know a characteristic capacity. We just need to show computable characterization. So it's enough. So as I said before, it's enough to see if you can show it for every channel. If it doesn't increase from 1 to 2, then you're done. Right? Because it doesn't increase from 1 to 2, 2 to 4, 4 to 8, you're done. That sequence. Or if you show that there is one channel for which this doesn't hold, then you mainly show suboptimality because you could achieve this rate. Do you understand what I'm saying? What I'm saying is that if I could use the same strategy for 2 time slots, thinking of a new channel, it's an achievable rate, considering 2 time slots a new channel. Okay? If that beats the one channel representation, then I'm normalizing by a factor 2, then it's suboptimal because I can achieve this rate. Okay? If it's not, then because the n-letter goes to capacity, I've proven it's optimal. So the point I'm saying is, you don't need to devise a new strategy to test the optimality, suboptimality. Okay? You already have the power to test the optimality, suboptimality. And I'll tell you why it has not been tested. Okay, but we did test this. We spent a lot of time. And so this is a new result. It's like last 2 months. We showed that for interference channel, it is not optimal. We showed that the Han-Kobayashi is not optimal. And you'll see later why the real difficulty is coming up with the class of channels for which this beats. Okay? So at least one of the things we know is not optimal. And this is really a power computation which was not there in the early 70s, mid 70s. We have a lot of computational resources available for us. Okay, really. And there's a lot of theoretical results that make such computation feasible. You cannot do it simply. You need to have some idea of what's happening to get this. So this is a new, I will not talk about this, but I want to say that this technique I said is useful to solve at least these problems. Okay? Or at least get intuition. Okay, I spent a lot of time in the broadcast, and as Max said, I tried for some time to get intuition, just to get a feel. I'll tell you what I tried. And for broadcast, it appears as if this holds. Okay? It appears, so this has been going on for, we did it for a few months, we couldn't get a counterexample. For interference, we could get the counterexample quickly. It's not true for broadcast. And for broadcast, we know much more than interference. At least I know much more than interference. Okay. So that's the, okay, so let me tell you, so I'm going to focus mainly on broadcast because interference we are now back to square one. We have no clue how to proceed. So at least that's clear. Now broadcast, what do we do? So capacity of broadcast channel is unknown in general. However, for special class of channels, it has been characterized. Okay. And these blue things are what I'm going to talk about in this talk. You're going to see. So first for degraded channels, and then you heard this word less noisy in Joe Barrow's talk in the morning. Okay. Joe here? No. I hope. So don't take the definition of less noise in this slide because he has small typo. Okay, that's not the definition. The definition is slightly different. So, but this is it's a very nice paper. This is a very nice paper by Janos and Kati Martin. They won the Chandra awards back to back last 2 years. I mean, not this year, the previous 2 years. And then there's more capable. So these are all like increasing class of channels. So less noisy is more than degraded. More capable is more than less noisy. This is all by Abbas al-Gamal. Then I extended to what is known as essentially less noisy and essentially more capable. Then there's also product of reverse degraded. So these are all increasing, but this is a different class, product of reverse degraded broadcast channels with by Abbas. And then we showed several classes of broadcast channels. The point is it includes everything here above and more. So this is kind of the meta result which includes more, and this has some other results inbuilt. But there's another class for Gauss. These are for discrete channels. For Gaussian, there was a very nice paper which won the best IT transaction paper award. with the vector Gaussian broadcast channel with private messages, you're going to see the result in a very simple way in these two talks by Weingarten, Steinberg, Shammai. And then this technique could not be used to show when you have private and common message. I'll tell you what this problem is. And we're going to show the technique I'm presenting works. That's the reason why this technique was invented is actually to go from this problem to this problem. We tried to extend this technique, or we tried to get the intuition. We said we couldn't go anywhere. We went back to the drawing board. We tried to see what they were doing, and we came up with this technique. That's the history of this technique. Okay, so let's start with the very simple setting. Okay, we're going to start with what is known as a degrade broadcast channel. A degrade broadcast channel is a channel where, this again was talked by Barros in the morning, where the receiver Z hears a strictly noisy version of Y. Okay. And the capacity region is the union of rate pairs R1, R2 that satisfies these two constraints for some U. U is a random variable that you've not seen before. So this is called an auxiliary random variable. You take any U such that U to X to Y to Z forms a Markov chain. You compute this region as a rectangle. You take the union over all possible U's, and then you get the capacity region. Is that clear? So I hope that's clear. So this is very simple. What I'm saying is something very, very simple. For every U you get some. For every U you pick, you get some rectangle, and you get some other rectangle. You get some other rectangle. You take the union, you get the capacity. Okay? You should be aware that there is a problem with this, right? The problem with this is you don't know which U's give you the best regions. You have to optimize over all the possible U's to get this. So it's a good representation. It can be computed in some finite time, but it becomes harder and harder. It's not even clear what you optimize it. For some cases we know, for Gaussian we know, we're going to show the proof here. For some other channels we know, but in general it's hard. Okay? So for Martins and Hahn-Kobayashi, it's much more complicated than this region. So it's very difficult even to evaluate this region. Forget comparing one letter with two letters. Okay? So and the freedom is in choosing PUX. Achievability is achieved by something called a superposition coding. Max talked about this, not the focus of this talk. The capacity is convex by time sharing argument. But the most important thing for convex region is that if I have a convex region, I can characterize by supporting hyperplanes. Do you understand what I'm saying? I can characterize the convex region by intersection of supporting hyperplanes. Okay, that's what I'm going to use there. Okay, so what are the obvious boundaries of capacity region? It's clear that R1 must be at least 0 and at most point-to-point capacity. R2 must be 0 and at point-to-point capacity. So what are we interested in? We are interested in characterizing these hyperplanes. We are interested in characterizing hyperplanes of this type, right? Where these mean. So you're interested in characterizing R1 plus lambda R2. Okay? So one way to say is that the maximum R1 R2 element of capacity is the maximum over all joint is P of Vx, Ixy given V plus lambda IVZ. That's an alternate expression. For every lambda, if I know that this is a hyperplane maximum, then I can get the intersection. Okay? And you have to look at V less than X. So this is the representation I'm going to use. So I'm going to use a hyperplane representation. I'm going to say what is the maximum. I'm going to show that factorizes. Okay. Okay. So I'm going to show why is this an outer bound, or why is in fact the capacity, but I'm going to show why is an outer bound. Again, that is single-letterization. Why am I going to single-letterization? Because the proof of this for the Gaussian already involved what is known as entropy power inequality. Okay, and we're going to show it without using entropy power inequality. What is entropy power inequality? Entropy power inequality is a very nice inequality. It says that if x and y independent random variables with a density function, x and y independent, they have density, they are continuous variables, then 2 to the power twice h of x plus y is bigger than or equal to 2 power 2 h of x plus 2 power 2 h of y. It's not a very, okay. When I teach this proof, it takes about at least an hour and a half to prove this, so I'm not going to show the proof here. It's a very nice, the proof can reduce to a few pages, but I don't think you'll see that proof anyway. It's a very nice kind of argument. It's a Gaussian perturbation argument, a very nice argument. But you want to use this, and for later things, even this, you have to use some advanced versions of this. Okay? So this is not by no means is an easy inequality to prove. But you will see here we get for free. Okay, so how do I show? So from Fanau's inequality, I'm ignoring the epsilon terms in the error. R2 is at most 1 over I m2 Zn because Zn can decode m2, and R1 is at most I m1 yn given m2, and I get Ix. Okay, what am I using here? How do I get this? Data processing. This is just data processing inequality. Okay, second inequality for the data processing. So maximum of R1 R2, I can clearly it's at most equal to this inequality. It's less than the equal to. Why? Because I can put V to be M2 again. Type of V to be M2. Right? It's I x and y given M2 plus I M2 Cn, so it's V to be M2. So in the next slide, I'm going to show a single-letterization argument by Gallagher. It's really the only technique that we know to prove conversions or upper bounds to such expressions. It's really the only technique. So she developed this in 74, and 40 years now, and we don't know really any other technique. It's really the only technique we know. Okay, how do we show this? It's a very nice argument. So we want to show that the maximum of such an expression, half times this, is less than maximum Ixy given V plus lambda IVC. Again, the purpose of showing this is to see such an argument because it's a school, so you can at least learn something, and then you can also use this to Gaussian optimality. How do I want to show this? Okay, let's go slowly. It's not hard. It's really, if you get so this is what we start with. This is just, I'm expanding the first term by chain rule. Okay, I'm dropping some terms, but you want to show this. I put a blue equality here because it's true, and you can take an exercise to show this. Okay? Is the Boolean slice? It's very easy to show. You can get this. With equality, again in another equality, you get this term out. So it's Ix, you put something here. Okay, here what did I do? I put a Z1 here. And the reason I put a Z1 here is because Z1 is a noisy version of Y1. So I given Y1, Z1 is giving you some new information to the rest of things. So that's why I put this, I use the degraded version. Then you can do this. So what I do from here to here, Ix1 given V, I didn't do anything. Okay. So I should remove. Anyway, so you get this. Observe what happens here now. So what happens here is that I get equality which says that I have Ix1 y1 given V plus Ix2 y2 given V z1 lambda V z1 V z1 z2. Look at these two expressions. This must be less than maximum of this because this is the single channel. Now look at this expression. This is a new V. Let me call it V prime. This is less than 1 times maximum of this. Like this. So this plus this is less than 1 times maximum. This plus this is less than another maximum. So these two are less than. So half times is less than maximum of this. These are negative quantities. Okay, this is an equality. So you massage it in this form. Okay, now what do I do? Now what is the Gaussian degraded broadcast channel? So you have Gaussian, you have one receiver receives a noisy version, the other receiver receives a slightly more noisy version, and the capacity I want to show is this compared with this is very easy to show, and Bergman's showed, this is shown even before Gallagher's result, that it suffices to consider x to be u plus v where u and v are Gaussian. That's what we want to show without using any more techniques that we already introduced. Okay, this is what we want to show. So how do we show this? So let's take d to be the maximum value of this optimization problem, subject to power constraint, and we call v star next star to be the maximizer. I'm not going to tell you why that exists, but it does exist. Now let v1 x1 and v2 x2 be independent identical distributed according to this maximizer. So if I take independent copies, then I get 2d to be just this equality because they just break up, they're independent. Okay, 2d is this, that's immediate. as before, let me do this. Let me take the plus minus thing, rotate by root 2, I get this. This is Gallagher's single-letterization. I took the last line out. So we showed this. 2D was exactly this because it's bijection. So it's exactly this. So you get this and you have these terms. So this must be 0 and this must be 0. Right? Because this is at most D, this is at most D. So if the whole thing is equal to 2D, then this must be 0 and this must be 0. If this is 0, we already get that Z1, Z2 must be Gaussians. Hence Y1, Y2, and X1, X2 are Gaussians. But that's not enough. Why? Because we also need to show the conditional distribution is Gaussian. How do we get that? So we get that. So look at this. So V1, V2. From this equality, I claim that we have this equality. Why? Because I take Z plus to this end, it's 0. So if I have Y plus Z plus Z plus sits behind, so you get Y minus Z plus, you get this equality from this. You can check it. Please do check it. It's very simple. And if you have this equality, now you see that there are two Markov chains, Y minus Y plus Z plus, Y minus Z plus Y plus is Markov, and you can see that they are positive joint density function. Therefore, Y minus must be independent of Y plus Z plus. Okay. So this is we will see a much simpler proof of this later, but you can get even from Gallagher's single-letterization that just Markov. So this is a nice fact if you didn't know, that if I have a triple of random variables for which there are two different Markov chains. Why there are two different Markov chains? This is a noisy version of Y plus, but from here I have this. So these two are Markov, and hence you get that Y minus should be independent of these two. Okay, that's a very. Please prove this. We haven't done this. It's a simple exercise again. Okay, but the useful facts to know. Okay, therefore they must be independent because so here I am conditional V1, V2, so it must be independent. Okay, I'm conditional V1, V2, their Markov chains hold, so they must be independent. So this must be 0. If these are 0, then from the exercise I gave you earlier, if the outputs are independent, the inputs must be independent. So I get x plus x minus equal to 0. Therefore, if xv is the conditional distribution, then we know that xv1 and we know that x1 v1 and x2 v2 are independent by construction. But we also have that x1 v1 plus x2 v2 and x1 v1 minus x2 v2 are independent from here. Therefore, these two must be Gaussians with the same variance p prime. They can have different means, but they must have the same variance. And with p prime must be less than the power constraint. Thus, the conditional distribution maximizes as Gaussian, and I claim that's enough because then I can have u plus v. Okay, this is so you can, as an exercise you can see why this you're done. Okay, this establishes Bergman. So you use the fact that okay, this might have been a bit fast, but okay. So you lost me somewhere. Where? Here. Okay. So okay, maybe I'll do it on the. Do you want me to do it more? This okay. Do you agree that this is a Markov chain? Because Z plus is what? It's Z1 plus Z2 by 2. So they are noise Gaussians, they are independent. This is a Markov chain. And therefore, we know that this is 0. Okay? What does the 0 give? What does it give me? It gives me, okay, maybe I should do it in the board. So, tell me if I'm getting it wrong, y minus y plus given v1, v2, z plus is 0. That's what we have, right? So which means like y minus y plus z plus given v1, v2 must be equal to y minus z plus given v1, v2. You agree to this or not? Because what I'm doing is I'm using this fact and chain rule to say that this must be equal. Because this is, right? So what is this? This term is this term plus this term. But this is 0, therefore this must be 0. Yeah? Okay. But we have the Markov chain, so z plus, given y plus, z plus is just dependent y plus. Okay. Therefore this is equal to, by Markov chain, y minus y plus v1 v1 v2. Okay, because z plus is a noisier version of it, so this must be equal to this. Okay, that's how we get that one. So I did the exercise for you. So it's very simple, it's just an exercise. Check it. So 0. Now what do I claim? I claim that this implies two Markov chains. Okay, clearly, I mean, so I'm conditional v1 v2. So here I'm conditional v1 v2. This implies a Markov chain that y minus is z plus y plus is Markov, right? This is just from this fact. Conditional v1. This is just from this fact. Okay. Why do I have this? Of course, this is trivial from channel structure because e plus is a noisy version of y plus. So I have two different Markov chains, and you have two different Markov chains, and this is even true for discrete. If every triple has positive probability, then this must be independent of the other two. It's an exercise you can check. But you need the positivity. If you don't have positivity, it's not true because you can put y plus equal to z plus, right? Then you don't have independence. But you need the positivity. You can't have things collapsing into a smaller space. Okay. So is that clear? Or you can read. So now these outputs are two channels. The outputs are independent. The inputs must be independent because they're Gaussian noise channels. So therefore we have this, and therefore we have that they're independent. So now the last part is what? For every v1 v2 they're independent. Okay. So if I put little v1 little v2 they are independent. So because they're independent, they have the same covariance. The covariance cannot depend on v. The mean can depend on v, but the covariance cannot depend on v. Okay. So then x can be written as some u plus v prime. X is Gaussian and v prime is Gaussian, so u becomes Gaussian. Okay. That's basically the thing. Okay. So this is now you can reason why is Shabbat Bergman. It's now you're done. Okay. This is the main reason. Okay. The traditional argument, as I said, uses entropy per inequality, but Bergman's didn't use single letter. He could work from n-letter form because there's an n-letter form of entropy per inequality. Okay, so you don't need to go through this. Why do I say weak? The reason I'm saying weak is because for this proof you only need entropy per inequality when. So you only need this form. You only need 2 power 2 h of y plus z bigger than or equal to 2 power 2 h of y plus 2 power 2 h of z when z is Gaussian or independent of y. Okay? This is a bit easier to prove than when this is not a Gaussian. Okay? And in fact, one of my favorite results is Max's result that 2 power 2 h of y plus square root tz is concave. In t, this is right? Cos the 85. And there's a beautiful proof of this by Cedric Villani, who's a fields medalist. It's a very elegant proof. Not that I have anything against Max's proof, but it's a beautiful argument it's just 2 lines. He just breaks up the proof into 2 lines. Okay, and then so this is a traditional. So this is how they show. Okay, questions about content so far. Is your picture clear? What am I doing? I'm using single-letterization, which is a discrete argument. I'm going to show that it gives me for free by this rotation trick the optimality of Gaussian. I don't need to do anything more. I don't need to be fancy. Okay, this may be a good place to stop, may not be a good place to stop. Maybe I'll tell you what I'm going to talk about later. So what am I going to talk about on Friday's talk? I'm going to show how this technique can be used to solve the vector Gaussian broadcast channels with private messages, and also the vector Gaussian broadcast channels with private and common messages. And I'm going to tell you what are the other applications of this technique. So you have a hammer, so people have started using this hammer. So what are the hammer? So I know next Friday's talk is the last talk of the workshop, so there might be a lot of people who may not come and who may be too tiring. So let me just tell you what at least the problem definition, and then I'll come back and repeat it on Friday. What is the problem definition? So what is with common message? Common message means that there are three messages. M0 is required by both, M1 is required by one, and M2 is required by two. So this is the broadcast channel with the common and private messages. And your goal is to compute the capacity region or the set of achievable rates R0, R1, R2. Okay, this is in fact it's more harder than without common message. So what am I essentially going to show? Okay, the two slides I'm going to show is this will tell you why things are hard. Okay, this is open for discrete memory channels. It's solved for vector Gaussian channels, and we can see how it solves for vector Gaussian channels. Okay, I told you that there are regions whose optimality is not known. So this is the region for broadcast. It's called Martin's region. It's a very nice region, but it's a set of all rate triples satisfying these four constraints. Okay, you take any triple UVW to X such that this Markov chain is true. This is a channel, so there's no freedom here. But such that this is true, you can compute this region. When you take the union over all these regions, you get the Martin's achievable region. Now you see what is hard. You have UVW, you don't know what UVW to choose. It's really, really hard because it's very hard. And she didn't even have a bound for the cardinality of UVW. Okay? And I spoke to her for length about various things, and she was telling me that when she discovered this region, she was actually working on the deterministic broadcast channels in parallel with Gelfand and Pinsker. She had a solution for deterministic channels, and she thought that this was a very natural generalization strategy for deterministic channels. And she thought there was no reason to believe that may be optimal or not optimal. And in fact, my first attempt was to show that this is not optimal by trying to find a channel for which the two letters is better than the one letter. And if I can show that, then I could show that it's not optimal. Okay, that I couldn't do for 2 years. Okay, it took me a long time to compute this. But even now we don't know if it's optimal or not optimal. If you ask me to bet on it, I'm more inclined to believe that this is optimal than not. Okay, and the reason for that is there's so much of beautiful structure that's coming out. Maybe this is not the best way to represent the region because the region is just a union of these. Maybe there's a different way to represent the region, but I think this gives you the optimal thing. And they're very nice stuff, but it's not the topic of this talk. So there's an outer bound. I call it the UVW outer bound. So there's an outer bound for the broadcast channel, which takes this form. Okay, so it's minimum. So this seems similar. It seems in fact weaker than inner bound, but it's in fact an outer bound. But these terms are bigger. So what I'm going to show on Friday is that for the Gaussians, these two bounds collapse. They evaluate the same region. That's how the capacity is shown. Okay, for the Gaussian channels, these two become exactly same. So you know the capacity. In general, we know after a few years of work that these are not same. For discrete, they are not the same. Okay, so this technique will not go for discrete. But for Gaussian, miraculously, it's true. And again, Costa has a role to play in this from his old paper on dirty paper coding. We'll come back to that on Friday. But that's the strategy on Friday. We will evaluate the outer bound using the outer bound is a single-letterization algorithm. We use it to show the Gaussian is optimal for the outer bound, and we show that's achievable. So that's the strategy. Okay, that's why single-letterization are useful. So we will evaluate the outer bound and show the Gaussian. It requires a bit more of tools, but not much more. Okay, that thing on we will do on Friday. Okay, I'm done. Questions? Any questions? No. It's too fast. This clear?
I have a question.
Yes.
The issue with the Hana-Kobayashi region, so it's probably not optimal for interference channel. How about for Gaussian interference? Does that
I don't know. I mean, okay. Max asked me the following question that I told him separately that So the result we showed that Hahn-Kobayashi is not optimal for the interference, discrete numberless interference channel. But he wants to know two things. He wants to know whether it's optimal for the Gaussian, and he wants to know whether the Gaussian signal is optimal for Hahn-Kobayashi there. Okay? So I don't know the answer. But the technique I'm telling might not work because there's a conditioning, and conditioning kills some optimality of Gaussian. If I were to venture a guess, I would say no, but I don't have a proof. Okay? Though that's against all the evidence that we have. Okay, it's evidence against all the evidence that we have, or all the things that we can show. In parts, it's optimal, but I would venture that some parts that we don't know, things are more tricky. Okay? Things are more tricky than what we can prove. That's but this idea of 2 to 1 is very. I think the 2-letter 1-letter is very useful because if you look at converses, they are actually big messes of inequalities. But if you just show 2 to 1, it's actually very, very simple. It's if you make converses very, very simple, just few lines, and it's not very hard. Okay, that's all. Other questions? Otherwise, there's a poster presentation. I think. I don't know. No, I'm done.
Okay, so thank you.